Hello again, folks. Today, as promised, I'm going to go over the solutions for test number 2, which would have consisted of Chapter 5 and Chapter 6 material. Today is, where am I? Today is Tuesday, November 9th. No, I think that's the wrong channel. I'm sorry. I'm looking at the wrong channel there. Today is Tuesday, November 10th. Geez, I'm in a time warp, huh? Tomorrow's Veterans Day. That doesn't affect our class schedule per se. On Thursday, we'll start with the remaining material, which begins with Chapter 7. All right. What you should be doing ideally between now and then is the remainder of the assignments from Chapter 6. All right. So I want to say 6.1, 6.3, and I forget what it is, 6.5 and 6.6, I think. All right. I typed it in announcements, of course, but especially those last two, 6.5 and 6.6, they're due Thursday. Work on those because you need the experience with the material. This stuff, as I said, unless I could find a way to administer a test remotely, legitimately, and not in person, I can't see. I figured what I would do is I'll just simply, I made the test, right? And this is available in announcements for you to print out, right? And I'll give you credit for it. Okay, so you don't have to hand anything in, but when you have the time, do your homework first. All right, we'll go over these solutions. Okay? I'm being hailed. No. All right, let's go over these solutions. There's 25 problems, and they're all multiple choice. So the solutions are there. You could probably figure anything out yourself. If you trust yourself, and you should. All right? But I want to walk you through each of these. Okay? I don't know if the overhead light is necessary. Nicely for once. Okay. This is my new marker. Okay. It's really tight. Alright. Focus signal. Alright. The first one is, let me just hold this and save myself trouble. To convert from the standard form of a quadratic equation to the general form. Alright. Remember, this is the standard form. I think this might be a little too faint. It'll take a while for this to get broken in. If the light makes a difference. I think that's worse. Right. The standard form looks like this. Later on it resembles the transformation model. Right. It's partially factored. That is, it doesn't incorporate this term here. Right? And what you need to do is to convert this to the general form, which looks more like this. Right. And the actual problem is this. 2 would be in position of A. This is going to be plus instead. There's a 1 here in place of H, and a minus 6 here. Everything else is in position. Right? It's squared, so it's quadratic, and we need to make it resemble this. A couple of things. All right. Converting from standard to general is easy because really what you just have to do is expand this, which more or less means FOIL it, because it's a binomial times itself. And then, if necessary, distribute and simplify, right, so that you end up with 3 terms like this. So you have x plus 1 squared. You could certainly write x plus 1 times x plus 1, and then proceed with FOIL. In other words, this times this times that, this times this times this, or recognize that this is going to behave as the perfect square trinomial model from factoring, which predicts that The two outside terms would be squared, and if it's x, then it's x, and if it's 1, it's 1. And the middle will be twice as much as the two outside. So whatever your terms are here, x and 1 in this particular problem, would be multiplied by 2. And if this is the positive incarnation of this, then this is this. Right? Whether you did it that way or you did it brute force is totally cool. All right? But just realize that this is what the outcome should be. Let me write this in a different color. Let's see. You have x squared plus 2x plus 1, because 1 is squared. And there's still this minus 6, and there's still this 2 hanging on in the front. Of those two things, you really should do the multiplication first, because you're basically simplifying an expression. I know that this is part of an equation, but if you're sticking with just one side, think of it as an expression, so it follows the order of operations per se. Specifically, I should say. Anyhow, you would distribute 2 to each of these things, which means you end up with 2x squared plus 4x plus 2. Drop the parentheses, and there's still this minus 6. Right, which means that dead last, what you end up with is this. A function, that's very faint. Get it by green. I just bought a new package, so they take a while to break in. That's better. Okay. F of x is equal to 2x squared plus 4x, and then if you combine these two, you get minus 4. Which should be choice D in this case. All right, good. I'm sorry, I'm getting text messages here. Yes. I'm having a text battle with somebody that shouldn't. A family member. 'Tis the season, it's just nearly Thanksgiving. I'm sorry, I'm setting up an example. Make peace. It's a good thing. Alright, now 2 is doing things the other way. Incidentally, the vertex form, if you look here, remember what was given here is called the standard form. And what we converted to is the general form. These are the general form. I use the alternative phrase to go back the other way. If you're starting with this, which appears to be in general, you're going to convert to the vertex form. I personally just prefer that because of the confusion between standard and general. It really depends on whether you're dealing with a function or just a regular equation. Anyhow, vertex is indisputable. Here's 2. You're going back the other way. You have the function x squared plus 2x minus 8. Just remember, if necessary, sort of put the ghost model above it. Ax squared plus bx plus c. All right. And realize that these things immediately below are what they are. If there's no number written here, one would assume it is positive 1. Okay? If there happened to be a minus there, just make it negative 1. But anyhow, you need some of, well, at least 2 of these pieces here, right? When you're converting from general to standard, aka vertex form, which is the form that specifies the vertex of a parabola. Remember this, A is A, no matter what, right? So we already have A, we don't have to go hunting for it, right? H, right? And the reason that we want H is because we want, remember, this is the standard vertex form, x minus h squared plus k. We want basically these three features. H is really a stand-in for x, right? The vertex x. And it could be gleaned from plugging in B and A, right? Similarly, K is a stand-in for Y, and Y is really the function evaluated at X. So whatever this is, if you plug it back into the original function that is here, right, it will spit out what the Y ought to be. And then you could reassemble the equation, right, in this model, the standard vertex form, right, using these parts. Right. Anyhow, A is A, so we have immediately 1 in this case. If you stick 1 in this formula, and perform the arithmetic, and recognize that B is 2, then this is really negative 2 over positive 2, which reduces to negative 1, coincidentally. And then we're going to go back to the original function in blue there and evaluate it at negative 1, because that's what x is. And then you follow the order of operations. So you square first, then you multiply, then you combine these two, then combine the last two. All right, whatever's left over here. So 1 squared is just 1. 2 times negative 1 is negative 2. Do those first, you get negative 1. And then negative 1 minus 8. You should end up with negative 9. All right. So if I go to the standard vertex model and I insert 1 here, which is superfluous, you don't have to put positive 1, it's kind of implied. Negative 1 here, being mindful there's a negative in the model, and then putting negative 9 here, you're almost good to go. All right, the end result in its most concise, aesthetically pleasing form would be just this, x plus 1 squared minus 9, which should be choice C. Touch this slightly. Okay, moving on. Number 3 here. Given the vertex point and a point on the graph, write a quadratic function. The choices you'll notice are in vertex form. Right, they're just a more concise version of it. When you do this, where's my marker? Basically, start with the model. This is 3. A x minus h squared plus k. And insert the vertex immediately in the appropriate place. Remember, the vertex is, it's really an x and a y, but we call it h and a k just to specify its job, more or less. In the text, it says that this is really 2 comma 0. So in place of h, we would put a 2, and in place of the k value, we would put a 0, which means that it reduces immediately to this. Okay. Next, what we will do is take whatever other points that there's telling us about and insert that. So insert the second point, which is, in this case, 4, 12, and then solve for A. Okay, this was sloppy of me, but this is a function, all right? It might be more practical at this point to recognize f of x for what it is that it is y, really. It's filling the position of y in a certain notation. So this is really y is equal to a times x minus 2 squared. And in place of this, we're going to put 4 here and 12 here. We have everything we need to rearrange this algebraically to find a. So perform the inside work here. This is a times 2 squared. Do the squaring. This is really a 4. Right? And if you divide by 4, you get a is equal to 3. Right, which means that if you took all of this information, the a value and the vertex, and put it back into this model, you have the answer. So f of x, a, even if it seems redundant, let me rewrite this. And we'll put the appropriate parts in. All right. A is 3. Let's see, 2 goes here again, 0 would go here. The more concise way of writing it would be this: 3 times x minus 2 squared, which is choice B. Okay. Let me get a sickle glue up. I should just save myself a little bit of trouble and put that there. And move this over here. There we go. Alright, next page is 4. Alright, find the zeros, aka the x-intercepts, for this function. Okay. Alright, now when you do something like this, you want to factor it. I think I threw that hint in there. Right, okay. So, if you're given this is for 4. The function of x is equal to, let me pick this up. Why am I torturing myself? 2x to the 6th minus 12, x to the 5th plus 18x to the 4th. Let's attempt to factor it. Alright. Don't pay attention to anything but the right side. Right. Look for similarity first, right? That is the, what you might call the GCF style of factoring. If this was a trinomial, the guts that we leave behind in a factored form of this will have 3 terms as well. They'll just be reduced somehow. They evidently have the letter x in common, so we'll maybe start with that. The question is, how much x would they ever have? It turns out, even though it's a GCF, right, it's the minimum, really. That's the most that they will ever have in common. So a 4 goes here. Insofar as the numbers are concerned, you would, unless you could do this in your head, and that's fine, that would be cool. Consider the factors of each of these. Let's see, 6, 9, and 18. And then choose the greatest common factor of those things. Everything is made of 1, of course, but the GCF is actually 2. Okay? So if you rip the factor, that which these things are made of, out of each one of them, and put it on the outside, it's 2x to the fourth. Think about it backwards now. 2 times what is itself? It would technically be 1, which if you want to fill the void temporarily, maybe that would be cool to put that there. How about the x? If this is x to the fourth, you would need extra 2 x's in order to make x to the 6. Okay? And similarly, 2 times what is negative 12, negative 6. How much extra x do you need? Just 1. You could put the 1 or not. And 2 times positive 9. X to the fourth is already accounted for. In this slightly more concise way of writing it, x squared minus 6x plus 9, even that further still can be factored. And I wouldn't employ any special techniques. You can do this sort of intuitively. If this is a trinomial, that's 3 terms. Usually what a trinomial factors into is a binomial next to a binomial. And if it's x squared, it's probably going to be x here and x here. If it's 9, it's probably going to be 3 and 3. And the way that you would know for sure is that these two things, at least added, would make 6. Then as an afterthought, consider the sign combinations. If you want them to amplify rather than shrink out of existence, that is, to make things get bigger rather than smaller, you would add these. Same signs cause adding. If you want a negative, then they both have to be negative. And simultaneously, a negative times a negative is a positive. So now you have 2x to the fourth times the quantity x minus 3, and x minus 3 again. If you want, you could recombine these two and write them like this, as x minus 3 squared. Right? That's totally up to you. Right? Now, if we want to find the values that are the x-intercepts, what is true about x-intercept, whatever it is that 0 is the value for y. So we again recognize that f of x is really standing for y, put a 0 here, and we'll apply the 0 product rule, which means that I could divide out 2 actually if I want to do myself a favor. Right? Divide by 2, and now I have 0 is x to the fourth, x minus 3 squared. Right? This factor by itself, according to 0 product rule, could be the thing that equals 0. This factor by itself, x minus 3 squared, that could be equal to 0. Right? And you deal with them in almost a similar fashion. Right? In the case of the binomial, I really do have to put the parentheses if I'm going to write them that way rather than as 2 separate things. No harm done either way. If you're going to solve for x here, then you would have to multiply by the reciprocal power exponent. So if it's 4 over 1, you can cancel this by multiplying by or raising it to 1/4. Right? And then do the same thing here. I'm jumping the gun here. 1 to the over 4, which just realize is a 4th root of 0. Right? If you write it in radical notation versus rational notation. 0, the 4th root of 0 is still going to be 0. That's one of the two x-intercepts. Right? So we have 0 comma 0, the origin in this respect. And if you deal with this one, at least if I'm dealing with it simultaneously, these two like factors, I'm just going to go for radical notation here. The opposite of squaring is square root. Square root of 0 is just, again, 0. So what you end up with is x minus 3 equals 0. And then move 3 by adding. So x equals positive 3, right? Which means that a second x-intercept would be positive 3 comma 0. These two, which is choice A. Now for 5, got a little into theory here. Consider the multiplicity of this function, which ideally you would want to consider multiplicity when it's factored. So let me rewrite some of this. I'll get my markers again. I'll save myself the trouble and put that there. Alright. If I took this term here, 2x to the fourth, and then x minus 3 squared, this is completely factored. Well, it's debatable, I suppose, if I have this written concisely like that. But this is a factored form of the function. I can consider the multiplicity. All right, remember the multiplicity is deciding, it's called p, if you have a factor, we're looking at the exponent, and it's usually, this is for whatever reason called p. Multiplicity. All right. If you have an even versus you have an odd, right? Odd cross the x-axis, right? And evens bounce at the x-axis. In both of these cases, if you stare just at the exponents here, what is the nature of those? They're both even. That means if you were to graph this, it means that they don't penetrate the x-axis, they simply bounce off of it somehow. Right? They bounce. Here's the difference. If you had a function that goes through, this would have to be odd p. Right? If you have a function that bounces, whether it's in this orientation or that, it's tangent at a point. Then this is a bounce. This is even. I should spell bounce correctly. Sorry. Bounce. That's not a technical term. Tangency is the better word. Anyhow, they should be choice A, both even, 4 and 2, and the graphs bounce off the x-axis at each of those zeros. Don't lose the papers. Alright, that was 5. This condition here was 5. Let us do number 6. Number 6 is this picture here. All right, looking at the graph below and judging by the number of zeros, which are x-intercepts, the degree of the polynomial would have to be what? You have a picture that basically looks like this in 6. You have a graph and a funky function that seems to ride briefly. It's a little bit hard to draw this one. Again, I need to hold this when I do it would be intelligent. Okay. Okay, something like that. Superficially, right, how does it look? It appears to penetrate the x-axis here and to bounce at this point, right? So there are, if I just want to generalize, at minimum 2 x-intercepts. Looks like that's just for the whole graph since these arrows are pointing up and down. 2 x-intercepts. So 2 zeros. Right. There's a formula, and I wrote it here. N is less than or equal to the degree, d, number x ints, and d for degree. If you determine visually that there's 2 x-intercepts, then 2 is less than or equal to d, the degree. So that means that the degree is at minimum 2 or something higher. 2, this would have to be degree 2 or greater. Right? How come? Because there's this less than symbol, is the point is facing 2, and there's an equals here. And the open end is facing the D. So it will be choice A. Okay? Of those things. All right? A little bit of theory. The 7. If you're looking at the same graph, notice that there are arrows. So if you wanted to estimate the end behavior here, as the x value heads off in, this is x is headed this way, what's true about the y values? The y values are going to infinity, right? Right, so this is the negative infinity direction. As x, it's funny because when you write the answer, they're sort of doing it backwards, right? X goes to negative infinity. The function, which is really y, right, goes to negative infinity as well, right? If you consider the arrow this way, as x's go towards positive infinity, this is just simply for the reason that we read from left to right, that this is oriented like so. Right? It's unfortunate because of the picture, right? Where are the y's going? Up, right? So this is going to negative and that's going to positive. The function y is going to positive infinity. And this would be choice C in the choices. Okay. All right. Okay. All right. Now, problem 8 is polynomial long division. Looks like this. Let's see what the answer is. You really wouldn't want to do synthetic division, which is why I suggested use polynomial long division for this particular problem. Things that are this ugly might be a nuisance. You could, I mean, it is possible to use synthetic division for this. It meets the requirements. It's really contingent upon the divisor. But I had suggested trying it via long division. So here's 8. You end up with something that is stacked like so. It's a rational expression. This up 2x to the third plus 3x minus 4, and this is x plus 2. All right. If you do it long division way, which works for everything, the only caveat here is that you have to fill in a missing term. Notice that it goes from degree 3 to degree 1. So we'll write in the dividend here 2x cubed plus 0 because it's not going to hurt anything, it's just a placeholder. X squared, and 0 times that would still be 0. All right. Plus 3x minus 4. We need to fill that void in order to get through this work. And out here is x plus 2. Now, I always do my work here. It is the first term divided by the first term, which is more conducive if you write it in a sort of rational style. This is just one monomial over another. What is this reduced to? The 2 isn't going anywhere, but the x's will become x squared. I would strategically write that above the space that is degree 2. So 2x squared. The neatness, and ideally if you were writing this, you would do it on something that's like graph paper or at least loose leaf, right? Because you could keep it in nice margins, you know, ledger style. We need to figure out what we're subtracting. So we're going to have to multiply by the divisor in order to accomplish that. Think if you consider ordinary long division, what is in the quotient times what is in the divisor is the thing that goes here. A lot of times we don't even think about that, but that is actually true. So distribute. 2x squared times x is 2x to the third. That is no coincidence. That is entirely on purpose. 2x squared times 2 is plus 4x squared. We're going to put that here. Plus 4x squared. Now, here's the issue. We're not subtracting just one thing. We're subtracting 2 things simultaneously. So what you're really obligated to do is to encapsulate this in a parentheses, right, and distribute a negative as you're going through it. My feeling is do the first one, 2 minus 2, this cancels. If everything goes according to plan, that first thing should 100% of the time cancel. But then when you're doing the second one, do the multiplication here, right? A negative times a positive is in fact a negative. And then combine whatever you can here. Then obscure what you've just had and write the result here. 4x squared, drag down the next thing, and follow the process. Okay? In this case, now you have negative 4x squared divided by x, which leaves you with negative 4x. Again, put that up here in the answer, the quotient. Multiply by the divisor again. And distribute this and this. And you get negative 4x squared, not coincidentally. Negative 4 times 2 is negative 8x. And you put that here, negative 4x squared minus 8x. Again, because you're subtracting 2 things simultaneously, you want to encapsulate this, and don't forget there's a negative here as well. Okay. Now be careful again. Distribute the negative. A negative times a negative is a positive, which is why this will cancel, again, 100% of the time if things are going according to plan. And negative times this negative is the same situation, it's a positive. But it ends up being you adding rather than subtracting, so it's positive 11x. And we only have to do this one more time. Okay. So 11x divided by x. The x's cancel, you're left with 11. You're going to put plus 11 up here. Multiply that by x plus 2. And continue distributing. This is 11x plus 22. 11x plus 22. And we have to subtract again. So equals, encapsulate, negative sign. In this case, positive minus a negative, I should say a positive combined with a negative, this is going to cancel. A negative distributed, a negative times a positive is a negative. This is going to amplify, all right? A negative and a negative is a bigger negative. So you end up with negative 26 as a remainder. All right. Okay. Now, how do you write that? I need this space, so I'm going to erase some of this work above here. Up here we have the quotient, right? But there's a remainder as well. So we're going to write that adjacent, right? You could write this as negative 26 over, what you divide by, x plus 2, and that would be sufficient. Or the alternative is to basically move this negative to here and put a positive instead. So if you wrote it like that, that's fine. If you wrote it like this, that's cool too. Okay, they're the same expression, they're just, you know, stylistically different. The outcomes are the same. Right, and this should be choice A. I wrote it sort of forward slash. Okay. I think I need a cup of coffee, so I'll be right back. Pardon me, I have it on the stove right here. I need a little pick-me-up. The next one is a prime candidate for synthetic division. There isn't much adjusting that has to get done here, as in the case of this one. This meets the criteria. They both do. You could have done problem 8 with synthetic division as well. But what ideally you would do is make sure that the divisor, that which you're dividing by, meets these conditions. Number one, you want it to be linear equation, right, a linear expression, which means no worse than degree 1. You want the lead coefficient, right, to also be, that is the a value, if you will, in front of the x, to also be 1. And then whatever your constant is, you're going to reverse the sign. So if you have x plus some constant, you're going to write negative c. If you have x minus c, you're going to write some positive c. Right. Now, there's a skeleton that you, at least stylistic, this is how I was taught. You put a box over in one corner, and you make a ledger here, and then you fill in, I'm probably encroaching a little bit too much on what I've written here, but you put the coefficients of, just the coefficients of the dividend here. So in this case, if you have 2x cubed and 5x squared and negative 7x and negative 12, you're just going to write 2, 5, negative 7, and negative 12. 2, 5, negative 7, and negative 12. And immediately under the last thing, you have another little L shape here. This is the remainder box. I don't play hockey, but I know that there's a penalty box. I think that's the penalty box, right? I don't know how to ice skate, is the truth of the matter. The divisor in this particular problem was x plus 3. So I'm going to put -3 up here. This is the constant from the divisor. Right. So if it's +3, we're going to make it -3. Right. The beauty of this is that you don't get distracted with any of the letters. You're just paying attention to the numbers. All right. Now, if there was a missing term, right, as in the last problem, it didn't happen here, but if you went from, say, degree 3 to degree 1, when I did the long division, I threw a 0 in, all right, a 0x squared. You would put a 0 in here if you needed to, multiple zeros if necessary. It isn't in this case, it's pretty straightforward. Anyhow, the process works like this. Drag down the first thing, and then proceed to multiply these two things. -3 plus 2 is a -6, which will plop here on the line. All right. Then perform the arithmetic. One of each sign, subtract them, you get -1, and do it again. All right. -3 times -3 is +3. All right. One of each sign, subtract them, you get a -4. All right. Do it again. -3 times -3 is +12, which means that you'll have no obvious remainder, it's just 0. Okay. The last thing is you rewrite the problem 1 degree lower. So if the original problem was, that is the dividend, was x to the third, then you'll just write it as x squared using these coefficients. So this will be 2x squared minus x. You can put the 1 if you want, and then this is -4. And there's your answer. All right, and this would be choice D. Okay. Number 10 is a function now that is rational as opposed to just expressions as all these problems. All right, I tell you, the numerator is of a rational function reveals the x-intercepts. So in theory, if you were looking for x-intercepts from a rational function like this, you really wouldn't need to pay attention to anything. The reason being is 10. If this is the rational function, x plus 4, and it is sitting on top of x squared minus 2x minus 3, and what you're looking for is just the x-intercepts, otherwise known as the zeros. What happens with x-intercepts is that the y value is always 0, right? Otherwise, it wouldn't be an x-intercept. It wouldn't touch the x-axis, right? That means that a 0, this is y, that a 0 would be in place of y here. If you were going to manipulate this equation, right, to get this, even if it's not factored, over to the opposite sign so that everything is on the same tier, what ends up happening is that whatever this is, however complicated it is, it's going to every single time be multiplied by 0. Because we're looking for an x-intercept. So that means that this would go away, no matter what. So the numerator of the rational function is really all that is relevant. All right? And you just have this expression, whole 4 minus 4, x is equal to -4. Written in the style of an ordered pair would be -4, 0, which would be choice C. Okay. Now the next one, 11, same function that we've used, right? Yeah. the denominator of the same rational function reveals the vertical asymptotes, the places where x are not allowed. Because it's two-dimensional, it's not just a hole, it becomes a sort of an invisible barrier. Right. Using the same function, now focus by factoring the bottom only and considering domain restriction. Right. So, I'll erase this, rectify my little issue here. Right. Slap myself with an eraser, better than a tall mop, right? Just put that information back and proceed. I wish I didn't make a mess here. Good enough. The denominator only comes from, remember when you have domain restriction, what is the one number in the world you're not allowed to have as a denominator? The denominator cannot equal 0 because then it would be undefined. It'd be like dividing by 0, which is a mathematical impossibility. You can't do it. All right. Anyhow, what we would want to do is just exclusively pay attention to this, but in the factored form ideally, because it's quadratic. So, and we're just going to go, well, we were trying to use the zero product rule, but it can't be that. So we're going to figure out what it is not going to be allowed. This will tell us the vertical asymptotes. Asymptote. If it's x squared, this is an x and an x probably. And if it's 3, it's probably 3 and 1. And in order to get a middle term of 2, we would have to subtract. So we'd have to have one of each sign. One negative, one positive. The outcome has to be negative, so the larger magnitude has to be negative. Okay. Now we have two smaller equations. This should not be 0, and this should not be 0. But we're going to still go through the same mechanics here. Move 1, x is not equal to negative 1. Move 3, x is not equal to positive 3. These are the locations of the vertical asymptote. X, they're at x1 and x positive 3. If we were graphing again in a horizontal only, one-dimensionally, this would be a hole in the graph and this would be a second hole in the graph. Since we're graphing in 2 dimensions, what it means is that at the location of negative 1 and at the location of positive 3, instead of it just being a hole, there's this barrier. Vertical asymptotes. Okay? Alright. This one I did the same problem. How about that? Okay. For 12, same rational function. You can see how creative I am, right? Being sarcastic. Irrational functions are interesting among other reasons because they also have horizontal asymptotes. Alright? Or they might have a slant. Now, if you take this same function and you analyze it in these 3 conditions, we'll decide whether it has a horizontal asymptote or a vertical or a slanted one, a diagonal line. Definitely has verticals, we already figured that out. Alright, but, okay. In this instance, we need to look at a different portion of this. Alright. Basically, our eyeball, the all-seeing eye, right, is here and here. Right? We're looking at the degree. Right? The top degree, which is usually, as long as this is conforming to good etiquette, which is that it's in descending order, the top degree is what compared to the bottom degree? Well, if the top degree is 1, and the bottom degree is apparently 2, then this is the relationship. The top degree, pardon me, I'm losing my mind, sorry, is less than the bottom degree. So, according to these rules here, right, rule number 1 is really the condition that's being met here. If the top degree is less than the bottom degree, then there's a horizontal asymptote right at the x-axis, which is otherwise known as the horizontal line y equals 0. All right, which is choice B in this case. There is in fact a horizontal asymptote, and it is the x-axis, otherwise known as y equals 0. This is problem 12, and this was problem 11. The next problem is the situation that is the third type, when there's a slant. Okay. The denominator of a rational, no, I'm reading the wrong page, sorry. Use either polynomial long division or synthetic division to approximate the slant asymptote. Now the reason that you would have a slant in this case is this is your function for 13. The function of x is equal to x squared plus 3x minus 3 sitting on top of x minus 1. In this situation, right, again, if we were eyeballing, I didn't really ask you when I wrote this, but if you were looking here at the degree and looking here at the degree, right, the top degree is greater than the bottom degree by 1. Which means that you have a slant instead. Instead of a horizontal. What is a slant? It's a diagonal line. Remember from way back, right? If you have a diagonal line, right, and it's linear, it would have to be if it's a line, right? You would have this, y equals something that conforms to this shape, right? Y equals mx plus b, meaning that it has a slope which controls the pitch, and it has a y-intercept which is weirdly called b, right? Anyhow, that is why it has to be off by a degree by 1. It's a line, all right? All right? It makes it linear, right? Anyhow, let's perform synthetic division on this because it will be pretty much okay. You're going to get a remainder in this case, but you're making it. You're finding an approximate, right, which means you're essentially rounding. It's kind of weird to think of something that is an equation like this with a remainder. But you basically, whatever the remainder is, you just say, forget it. It's an approximate. Okay. So, if we follow synthetic division here, and we can, this is linear, right? It's degree 1. The lead coefficient would technically be 1. The constant is -1, so we're going to use +1 here. This is 1, +3, -3. So I'm going to write +1, +3, -3. And immediately below the 3, I'm going to draw another L shape. That is where, again, the remainder would go. If there is a remainder. Right. So, drag down 1 and proceed to multiply. 1 times 1 is 1, put the 1 here. Do the arithmetic. Same signs, add them. So you get a positive 4, right? Multiply by 1 again, you get positive 4, right? One of each sign, subtract them, you get a positive 1. And we go 1 degree lower. So if we're calling this a line, it's going to be y equals, right? 1 degree lower from x squared would be positive 1 x to the first, and then the next thing would be a constant naturally. And then there happens to be a remainder in this case, so it would be plus 1 over what you divide by, x minus 1. If you entered this in your calculator, you would get an ultra precise asymptote, right? A diagonal line, right? And that's cool. But if you're doing this by hand, all right, you would get the approximate and go, I have to get this, I'm not gonna mess with it. Unless you were gonna use it to generate points. You could just start plugging in an x value, see what the y is. This is sufficient, all right, if you're doing it by hand, all right? X plus 4 is a diagonal line, okay? Which is choice D. All right, moving on. Chapter 6, the exponential and logarithmic functions. All right, I give you one example of a word problem. And we'll go through that. So, in this case, for problem 14, Francis wants to save $2,500 to go on vacation. Not true, but okay. To the nearest dollar, otherwise round your answer. How much money will he need to invest in an account at 6.25% interest, compounding daily, in order to attain this goal in 4 years, right? And there's the formula for compound interest given. So, use green since we're talking about money. This is the formula. The amount in the account as a function of time. That is superfluous, but that's how it is written. We can always modify it. Is equal to P naught times this quantity, 1 plus R. I'm going to capitalize it just to distinguish it from N. Over N to the T. With raised to N to the T. Okay. A couple of things to remember. Principal is the original amount of money. That's what the P stands for. Principal. That's dollars, I swear. Okay. R is a rate, which is realistically a percent, but it's a percent either in the style of a decimal or a fraction. N is the number of times compounded. In a year. And T is years. Okay. So we really do have all of the information. I put these things in red on purpose because I didn't want you to have to, struggle to find them. It's a little hard to read. All right, you need this much information that is in red to basically insert them in this. You're going to have to rearrange it algebraically, but you could use your calculator certainly to get the specific answer. Now, the goal is $2,500. Okay. The amount of time is 4 years. The percentage is 6.25%. And it says daily, compounded daily. So this is a little arbitrary, compounded daily. How many days are there in a year? there are, if you wanted a whole day, 365 days. If you wanted to be a little bit more accurate, you would say 365 and a quarter, right? So that after 4 years, you get another whole day, right? I would, since they're talking about 4 years to begin with, use the more precise decimal 0.25, right, to input into this. You get a better answer, okay? So we do have to modify also 625 here if we're going to use it. It is a percentage, which means it means divide by 100. The effect is that the decimal point will be scooted over 2 spaces, and it's really 0.0625. So in here, you'd have 0.0625. And in place of the ends, you'd have 365.25. In place of time, you have 4. In place of p, we're looking for that. And in place of the function, the outcome, the amount in the account as a function of time, you'd have the goal. So $2,500, all right? It has to be rearranged algebraically to solve for the original amount that is invested in order to accomplish this, which is not too bad. What I would do is try to tidy it up a little bit, all right? You can get away with a lot, just sort of moving whole chunks around, all right? Here's what I mean. Since you have a terminating decimal, 0.25, and you're multiplying by 4, I would reduce that to something less ugly. All right? It's really an idiosyncrasy on my part. All right? And I don't like the ugly, complicated look of that, but I know what I can get away with. All right? So don't be afraid to take a little artistic license where it's feasible. So 365.25, all right, would end up with this just being the exponent of 1461, right? You'd get a nice whole number at least instead of this decimal here, all right? If you try to straighten this out, all right, it's going to be a little bit too ugly. It's not worth the trouble, right? But 0.0625 divided by 365.25, you'd end up with a terrible thing. So maybe leave it alone. It is possible you could make that into a fraction, and maybe it would be easily combinable with that, but that may be more trouble than it's worth. All right. Here's what I would do. I may arguably simplified it to the point that it is okay to deal with. Yeah. If we're going to solve for this p, have to move the thing that is attached to it. So these two things are essentially factors. One is in a parentheses. Yeah, it's ugly, all right, but it's being multiplied. So if I wanted to take this entire chunk, all right, and move it from here over to the opposite side of equals, I really just have to perform the opposite operation. So I would divide by this ugly chunk. All right, and then put it here. I will use my calculator eventually, but I want to tidy it up first. I only really belabored this point because I knew I could simplify that, right? Relatively easily. Ugly, complicated nonsense. It's not really nonsense, it's making money, right? Ugly, complicated guts here, divided by itself, cancels to 1, which leaves you with just the thing that you're looking for, the original amount of money. So you have P naught, the principal original amount of money, is equal to 2,500. There is one other thing that you could do if you want to. This is something that in theory, you could enter into your calculator right now and would give you the answer. If you want to tidy it up just to be anal retentive with me for a moment, you could do one extra thing. This is a positive exponent here, attached to this complicated base, but it is encapsulated. All right? All of this is being affected by this. So if you want to, stylistically, move this from a denominator to a numerator, You could write it like so. The $2,500, that is the outcome, times this quantity, 1 plus 0.0625, sitting on top of 365 days and a quarter, to the negative 1461. It might be, arguably, easier to type that in than maybe as a denominator, right? But it is just dealing with numbers, and this is just dealing with numbers, so it's good to go in either incarnation of this, right? The bottom line is, if you type this, you'll get this. The value for P is 1947.043 something into infinity, which is approximately, if you're rounding it for the sake of money to a nearest dollar, it would be 1947, $1,947. Okay. Next is 15. All right, this is an example of transformations. All right, this is pretty easy. Use your calculator certainly when you're doing this. Based on the parent function, and the parent function is f of x is equal to, it's exponential, so you have a base of 1/2 to x. Enter this into your calculator to see what it looks like. Clear this out. Right, so you'd have basically typed that. And if you need to, again, adjust the screen dimensions by starting with Z standard perhaps, and it will draw. Right, you have something that looks like that. Notice where this is hanging on here. It has, let me go back and make sure I wrote that right. It has a curve that looks like that. Okay, it's exponential. So, I just do this. I'm sorry about that creepy noise. You have a curve that looks like this, decay model, right? Because of the base being what it is, a fraction rather than a whole number, you get a decay. Okay. The actual problem looks like this. It is the same apparent curve, but it looks like this. All right. If this is the parent, and this is the transformation, right? We would have to do at least one or two things to get it to starting from this to end up looking like this. Let me remind you of the model. All right. Right. The transformation model that is adapted to exponential functions looks like this. I'm just going to stick with, well, I could use function of x. Plus or minus a times whatever the base is, and then x plus c plus d down here on the same tier. All right. A couple of familiar things. This is a vertical shift. Right. This is a horizontal shift. Having a negative here causes a vertical reflection. Having an A here would cause a vertical stretch or compression. Okay. All right. The other two situations, horizontal stretch, right, or compression, or horizontal reflection, would be controlled by the things here and here, but you don't really have to worry about that. All right. Now, I gave you a hint here. Let us deal with the reflection first. We want to follow the order of operations, so we would want to deal with the part that is being multiplied before we would want to deal with the part that is maybe potentially shifted. So that would be adding. Okay. So this, in respect of this, looks upside down. All right. So what would we need to accomplish that? All right. In order to get something to be upside down, we would need to incorporate a negative in front of the base. Now, there could, in theory, be a coefficient there that's not affected by the exponent directly. All right. So we'll try this. Go back to your calculator and experiment by putting a negative in front of this. Just see what the effect is. We can see if it gets matched. All right, so here we have the original function. I'm just going to type almost the same thing, but I'm going to put a negative in it, and then I'm going to encapsulate 1/2 just to get it out of trouble here, and raise it to the x. We'll see if that one condition being met makes the same graph. I want to see if I can get this to look like this just by sticking a negative in the parent function. And we'll hit graph. No, all it did, it was basically reflected vertically. That's to be expected, right? So, let's try to figure out how we can get it to be a little bit higher up, right? What this accomplished was basically just doing this. Getting it to run that way. Right? In both cases, the original parent function and in this reflection, there appears to be a horizontal asymptote. So, if we want that to simply now shift upward apparently, instead of it being here to being here, how many spaces would it have to be? This is unfortunately not on graph paper, but you can kind of estimate. Here's the x-axis, and here's where this sort of plateaus. It's in line with what appears to be 3. So if it's just a vertical shift, it is intuitive. So we're going to have a number hanging on the end of this. And since it seems to go from y equals 0 to y equals 3, what I would estimate is that there is this extra term plus 3 here. Okay. So let us see. If we do that one more time, if that could make it resemble the actual graph, the actual function. And we just simply type in the reflection transformation and now put plus 3. And now hit graph. And that's it. That's this graph. Okay. So that should be, this is choice C out of the multiple choices. Okay. All right. Remember, I'm fond of saying this because I believe it truly. If biology people, right, their tool that they're known for is the microscope. right? Our tool is the calculator. Right? It was invented by math people. And if you go back, even to the 1900s, pardon me, the 19th century, so the 1800s, people had been attempting to make calculators before there were electronics. Like Charles Babbage is famous as being a person who invented the difference engine. Right? It's for somehow solving polynomials, I want to say, just the coefficients. Anyhow, it's a steam engine, right? A mechanical calculator. It's actually an amazing thing. It's in England. All right, 16 is just getting used to logarithms now. Right, for 16, if you're given the log base 1/7 of the function, right, of the argument x is equal to 2, right? And you're asked to convert this from what it is, a log equation, into its exponential form. For lack of a more eloquent phrase, I say, draw the jelly bean. Right? So that means that, right? What is a base is always a base. Right? So if this is the base in your log, it's going to now be the base raised to the exponent of 2, right? What does it equal? It equals the argument. Right, so if the argument is x, and this is equal to x. And now you have an equation that, being that there are just strictly numbers here on the left side of this equation, you could figure out what it has to be. All right? It is, I really should encapsulate this, because the exponent is not just applied to the 1, it is applied to both of these. 1 squared is just 1, and 7 squared is 49. So what is the actual value? 1/49 apparently, all right, which is choice B. Okay. All right. Now for these that follow, basically 17, 18, 19, and 20. These are expanding, condensing, let's see, more or less expanding again, just using the power rule in this case, and expanding again, okay? So we'll go through these. So you have the log of, and it would be understood as being a base 10, but don't stress. 17a times 2b. This is partially factored already, right? If you're going to expand this, sort of a procedure that would be helpful is to try the quotient rule. That is not going to apply in this case. Then the product rule, and then the power rule, in that order. Right? In this case, you're really going to start with the product rule because there is no obvious ratio here, there's no line. Right? But I would reserve the power rule for last. Okay. So, this is, again, partially factored. Just realize that everything here is being multiplied. Right? Just for whatever reason, the original author of this problem, who I stole it from, basically had these two parts separated. Right? The product rule says that you could write this same base as a sum. Right? That's the product rule in action. The quotient rule would be there's a difference. All right, and it would be these two things to start with. You could go further with this though. You could, if you recognize that 17 is a coefficient of A and therefore our product, you could go a little bit further. You could say the log of 17 plus the log of A. And then the same thing here, 2 and B can be separated, log of 2 plus the log of B. Now it's a matter of preference, really. I think if you analyze the choices, they put the numbers basically in front. So it was written like this, putting the A here and the 2 here. Spin myself a little erasing. Right? That is completely expanded. Okay. The problem that is immediately underneath it is the opposite process. This is 18. If this is expanding, which is breaking into sums of differences generally, this is condensing, which is sort of crunching. All right, you have to start with, all right, log of base t. Don't stress over that. It's just not to specify. 96 minus the log of t, 8. Provided that these things are the same bases, and they are base t, whatever that happens to be. You can combine them. And in that case, the procedure would be like so. Right? Apply the power rule in that instance first, right? Then try the product rule, and then try the quotient rule. Right? So there are no obvious coefficients up in the front here, so there's no rearranging this to put the power here, the exponent here or here. They're not a sum, so you could rule out the product rule, and instead go straight for the quotient rule, which says that if you have a difference, you can combine these as one expression. Just remember, whatever is on the left, that would be on top. So it would be 96 on top of 8. Right. And being that they are regular numbers, 96 and 8, you could do the actual division here. As long as they work out nicely. If they don't work out nicely, if they're not divisible per se, then just try to reduce the improper fraction. In this case, I recognize it from multiplication tables. So this is log of base t, 12, right? Because 96 divided by 8 is 12, right? Which is choice A. Okay. I don't know what that noise is. Drilling? Next is, okay, this is really illustrating the power rule. Rewrite the log of, what is that, g? Yeah. G to the argument a raised to 1 over b, right? As a product. It's a little misleading, right? If it's a product, it means that it will have the exponent out in the front of it, technically, which means it's like a coefficient, right? That's really using the power rule. Don't be misled, all right? It is a product per se, but you are employing the power rule. Right? Log of base g of the argument a raised to 1 over b. Right? This is the power rule, which means that if you have an exponent here, you could write this as a coefficient. Right? And you should have 1b times the log of g. The argument A. Okay. No sweat. Now the one underneath it, 20, is expanding officially again, and it will employ a couple of different things. Here's 20. Expand. Okay. So you have the original expression is the natural log, ln, of the quantity, the argument y to the third, 0 to the second, and then the cube root of x minus 4. It's ugly, but don't be deterred. Right? You have 3 friends on your side while you do this. Right? You have the quotient rule, you have the product rule, and you have the power rule. Right? And if you're expanding, you might do it in that order. Try this first, it's not going to happen, then try this first. And then do the power rule second. Right? Yeah. Second, third. It's backwards from condensing, right? All right. There is no rational expression here. There's no line. All right. So no quotient rule in this case. Go for the product rule. So these things are factors. Right? They're just more or less disguised. I'm going to put dots here to make it a little more obvious. The product rule says that you could write them as a sum. They'd all have the same logarithm. This is a natural log, which if you wanted, you in theory could write it as log of base e, if you prefer. Right? Most people don't bother. Anyhow, the natural log of y to the third would be the first one, this is in the front here, plus the natural log of z squared, plus the natural log of the cube root of x minus 4. We'll come back to that because of the rational style we could write it in, notation-wise. Okay. This is in radical notation, which we could convert if we want to, as a convenience, to rational notation. All that means is that the exponent would be whatever fraction is made of the index here and whatever the exponent would technically be here. Okay? If it is an index of 3, that means that realistically this is 1/3. Right? If it was a square root, it would technically be a 2 here, and it would be 1/2. If there's no exponent written in an obvious way, encapsulating the radicand here, the guts, then assume it is 1. All right? So rather than write it like this, you could write it like that. Right? Now that we're going to apply the power rule, it would be more ideal to have it in the rational notation. So what we would end up with is basically this. The power rule says put the 3 in the front. 3, the natural log of y, plus put the 2 in the front. 2, the natural log of z, plus 1/3 the natural log of just the quantity x minus 4. Right? You could encapsulate it with 1, but it's not going to change it. Right? If you end up with something that is a binomial like this, don't be fooled. You can't really do anything with that. You're stuck with it. Right? Anyhow, this would be choice A out of the choices. Now we're going to take advantage of these properties, these rules, while we're trying to solve logarithmic or exponential equations. I try to give little hints as we're going through it. So, for this first one, let me point to it here. I hope this is not too redundant, but you have 21. Ugly, right? Don't be intimidated. Right. I shouldn't say that, it's not nice. Maybe I'm setting a bad example. If you were going to solve this equation, notice where the exponent is. It's an x. And then 1 over 243 is equal to 1 over 9. I really didn't have to encapsulate this, I just sort of did that intuitively. But these things that have an apparent exponent, you really should. Right? So unless it's just affecting the 1, it really is affecting the whole kit and caboodle here. Alright, now, when you have something that has, this is an exponential equation, evidently, because of the location of the x is the actual variable, the thing we're looking for. All right, what we're going to try to do, and have different bases, try to convert to the same base. Okay, so you have x here, and you have x here, all right? And evidently different things here. 9 and 81, you might recognize that there is a relationship between these things. So if you want to, without any hints thrown at you, maybe I would try to convert this to something that is at least 9. All right, 243, I don't know if that's necessarily going to work. The hint that I gave you is try to convert these to base 3s, right? If you did this, it would be the same as saying 1 over 9 squared at least. All right, that so far so good. All right, but 243, let's say that you took 243 and divided it by 9. Let's see if it works. All right, it might inch closer to it. It really should start with 3, which is why I gave you the hint, but I'm kind of curious now. 9 goes into 24 roughly twice, which is 18, and the difference is 63. All right, 9 goes into 63 exactly 7 times, which is 63, and it terminates. Cool. All right, so from this you would have at least 27 times 9, all right, which is great because then you could see, all right, at least there's a 9 in it already, and I happen to know that 27 is something that can be factored even further still. All right, what times what makes 27? Famously, 9 times 3. So now you have that, right? And then you go, this is suspicious, all right? Well, maybe I could break all of these things down into the prime number. That would be great. And you can, right? Because 9 itself is factorable to 3 times 3. So in this case, you would have 3 to the 5th. And in this case, 9 squared, which is really 9 times 9, this would be 3 to the 4th. And this would be 3 squared. All right. So now this is all everything converted to the same base, and it didn't end up being 9, it actually ended up being 3, which is great, right? It's a smaller number, all right, and it covers all bases. So what does that mean? It means that we have this really. It means that this is 1 over 3 to the 4th raised to the x. And this, the extra thing here, is 1 over 3 to the 5th, right? And this is 1 over 3 squared raised to this ugly 3x minus 1. All right, now we're going to pull some tricks. Remember from way back, all right? When you have an exponent attached to something, you could shift its location. It's usually on the top tier to begin with, doesn't even look like a fraction. You could move it down here by just changing the sign. So if it was positive, it becomes negative. If you want to just go the other direction, that's cool too. Just change the sign. Which means that you end up with this instead. 3 to the 4th above this line would appear as 3 to the negative 4. It is still encapsulated by this x here, but we'll come back to that later too. Same deal here. If you want to put this above the line, change the sign. This would be 1 over, pardon me, with the change, 3 to the negative 5. All right? And then this over here, scoop this up here, 3, negative 2, and the guts that are still there, negative 3x minus 1. We can now take advantage of something that's called the power rule of exponents. Exponents. Which means that if you have an exponent raised to an exponent, you could just multiply those. Which means that this is really now 3 to the negative 4x. This didn't have anything, so it's just going to write it as negative 3, 3 to the negative 5. And the same thing here, but remember it's two things simultaneously, so you're kind of distributing in this case. So you have 3 to the 6x plus 2 is the end result. All right. Now we can get into the more recent stuff. The rules of exponents are, let me point to it because it's worth mentioning. From this old handout. This good stuff from way back when. This is like Algebra 2, maybe Algebra 1. You might have seen this material. More recently, we had discussed properties of logarithms, which is this sheet. Right? And the reason that I'm doing this, which is converting an exponential equation to the same base, is because of it is a strategy talked about, discussed more recently from here, right, this handout. If you are given different bases, we're going to try to convert them to the same base. Okay. All right. Anyhow, these things, still the old-fashioned rules. They are the same bases. So the product rule for exponents says that if I'm multiplying the same bases, I can combine them by adding these, which means that this would reduce to 3, negative 4x minus 5. I could just join them together in one common base here. On the opposite side, there is still this. And now finally, the more recent thing, we have a situation where we have an equation, and the only feature here is a base 3, and the only feature here is a base 3. These are the same on opposite sides of this equation. This is therefore 1 to 1, which means that we could write a smaller equation that involves just this stuff, just the exponents. And now finally, this is what we end up with. We end up with an equation, negative 4x minus 5 is equal to 6x plus 2. Sorry. Move the x's around, move the constants around. I kind of like to have the letters over here, so I'm just going to do this. I'm going to move 6x. If it's positive, I'm going to subtract it. These would cancel. You'd end up with negative 10x. I'm going to move the 5 from here to here by adding. On the opposite side, you'd have positive 7. If I want to get rid of 10, I'm going to divide by negative 10, both sides. X is equal to negative 7/10, which is choice B. Right? All right. 22. Alright, 22 is this problem. Solve, this is another equation. Negative 9e to the 10a minus 8 minus 5 equals negative 41. Right? When you have an exponential equation that is base e, ultimately you could maybe apply the natural log to it, but before you do that, you want to isolate it. Isolate e. So I'm going to move 5 right off the bat by adding. And now you have negative 9e to the 10a minus 8 is equal to the combination of these two. One of each sign, subtract them. You're going to shrink this to 36, it looks like. And it will be a negative 36. That is a 6, I swear. All right. get rid of this coefficient of 9, divide by negative 9. Divide by negative 9, you get e to the 10a minus 8 is equal to positive 4. Okay. Now, if you have an exponential base e here, what you can do is apply some inverse properties. If you apply a natural log here to this, right, the effect is that this will be 1. Simultaneously, the power rule is ongoing here, and that would just tell you you could put this in front, which means that it would realistically be 1 times 10a minus 8, right, which is not changing it. Just realize you can only get away with this if you're consistent. If you applied natural log here on this side of the equation, you're obligated to do it to the opposite side, right? Which means that you now have this. You have 10a minus 8 is equal to the natural log of 4. Natural log of 4 is probably going to be an ugly decimal number, so we're going to leave it as natural log of 4 and move the stuff next to it. We're going to move 8 by adding, and then this is 10a is equal to natural log of 4 plus 8, and then we're going to move 10 by dividing, which means the whole thing would be divided by 10. I would not attempt to simplify. You can't affect the guts here, the argument of this function, by 10. Right? Just write it like that. This is what a is. It's not the most satisfying answer, granted, but you could certainly enter this into your calculator and you would get an answer, right? A regular number. Right? And this would be choice C in this case. Okay. Here's 23. Looks like this. Find the exact solution for e to the 2x minus e to the x minus 72 is equal to 0. This is a prime candidate for using u substitution. Right? Ideally, what we would want is a genuine polynomial, which this technically is not, but something that behaves as a polynomial, it simulates it. We would like something that at least looks like a polynomial in descending order. And I should be more specific. A trinomial, maybe, in descending order, which means that the exponents would be going down. That the first term and the second term are in fact the same bases, and that the third term is a constant, and that lastly the first degree is double the second degree. Right? It is trinomial-esque. It's not a genuine trinomial because it's not really a polynomial by definition if the exponent is here. But it kind of looks like it, all right? It's a first and second are the same bases, they're bases, and the third term is a regular ordinary number, a constant. And the first degree appears to be double that of the second. So, what does that mean? It means that what we're going to do is we're going to say, all right, e to the x, I'm just going to call it u, right? Hence u substitution. In place of this, I'm just going to fill in the void with u, minus 72 equals 0. When you're dealing with this one, it might be a little bit easier to look at it as x to the 2. Separate these into an exponent raised to an exponent, more or less the power rule of exponents backwards. And then you could put a u here in place of that. Right? The argument is that it is less ugly and complicated looking to factor u squared minus u minus 72 because it almost resembles x squared minus x minus 72. And therefore you would just go through this process. if this is something squared, in this case it's a u, it's a u and a u. If you consider the factors that make 72, famously 8 times 9, right? Well, if this is a 1 really here, 8 and 9 would work very nicely. Just gotta make sure that the signs are appropriate. If you want these to reduce, that is to shrink to 1, then subtraction has to occur. What causes subtraction is one of each sign. One thing is negative, one thing is positive. If you want the outcome to be negative, the larger thing has to be negative, magnitude-wise. So this is plus. All right? And now you could solve this by zero product rule. If it is 0 plus 8 is equal to 0, and 0 minus 9 equals 0, then you have two teeny tiny little equations, which you can manipulate pretty easily, right? Move 8, it becomes a negative. And in this instance, you would have u is equal to negative 8. That one is dud. If you move 9, you would end up with u equals positive 9. Right. Now, why is that one a dud? Because if you back substitute, that is, if you take what u actually represents and put back what it represents as ex, then this is e to the x is equal to this, and this is e to the x is equal to this. Right. Watch what happens. E to the x is equal to negative 8, and e to the x is equal to positive 9. In order to solve this as before, you would apply a natural log, right? The reason why you should be suspicious of this thing that is negative is, in theory, this is standing in place of a y if it was an equation, right? The exponential function, right, looks like that. Y is never negative in those cases. So that's probably going to be trouble, right? I'm going to go through the motions anyway, and whether you feel comfortable with that or not, watch what happens. You would apply natural log for the sort of cancellation effect. This is 1, and the power rule would say put that in front. So this is really x. And if you attempt to enter this into your calculator, look what happens. The natural log of negative 8 gives you an error message, right? It's not a real answer, right? That is a dud. You see a negative here, be suspicious. This is a dud, right? It's extraneous, so technically, I guess, right? However, if you applied natural log here and here, there's no problem. This would end up being x is equal to the natural log of 9, right? And that is the one answer, which is choice C. Right? Two more of these and then we're done. I only have time, almost 2 hours. Here you have a genuine logarithmic equation, right? Now as a strategy, let me just point to something. A while back, right, I had suggested you do this, and I still mean it. A couple of things you can do. You have a situation sometimes where you have log on both sides. And as long as they're the same bases, you can take advantage of one-to-one property. That's not going to happen in this case, because it's just log here. Right? If you have a log equals a number, as you have in this situation, right, we'll attempt to isolate it, right, and then attempt to translate it into an exponential equation. And if necessary, we could try to apply some properties as well. So let me move stuff around. Okay. Start with what is familiar. Move 7. All right. Via opposite operation, you end up with 4 times the log of the argument 2n. Incidentally, what's the base here? If it's not written, you assume it is 10. Right? And it isn't necessary to write it. One of each sign you subtract, really. That reduces to 4. Take the sign of a larger magnitude, it's a negative 4. All right. Divide by 4 to isolate. And now you have the log of the argument 2n, which is, the n is really what we're solving for, is negative 1. Okay. Now, at this point, right, it would be to our advantage to convert this to an exponential equation, right? Which means draw the jelly bean, right? I need to put the base in here. If it's a common log, then don't bother to write it. Sort of like a lot of times math people leave out positives or 1s or 0s, right? Base log, pardon me, the common log is base 10. So if I now draw the jelly bean, all right, this is really 10 to the negative first is equal to whatever the argument is. You read counterclockwise. 2n. Okay. Divide by 2. And now you have n is equal to 10 to the negative first over 2. This could be cleaned up, right? If you have a negative applied to this 10, remember that just means that you could shift location. If you have a negative here, it means put this on the bottom, right? It just becomes a factor adjacent to what is there. So this would be 10 to the first, technically. Which means it's 10, and therefore 10 times 2 is 1/20th. And that is the answer, which is choice B in this case. No more. If you have log of the argument 4x squared minus 10 plus the log of 3 is equal to the log of 51. Right? These are all base 10 problems again. Right? When you have a situation like this, that you have not just a log on one side and a log on the opposite side of equals, but you have a bunch of stuff. Right? Try to condense first, rather than factor. And in this case, when you're condensing, remember you want to try the power rule first if it's possible. All right, then the product rule, and then the quotient rule in that order. Okay. So there are no coefficients in front of these. There is a sum, so the power rule, pardon me, the product rule is what we'll be combining. These would reduce to the same, as long as they're the same bases, they're common log base 10. All right. This would be 3 times 4x squared minus 10. On the opposite side, you have log, that's a fun way to write that, log of 51. Okay. Try to combine what you can. Distribute 3 to these two things. Then you'd have the log of 12x squared minus 30. And log of 51. I might be jumping the gun a little bit on that one. What I should have said probably to myself is that, these are the same bases. So this is 1 to 1. Which means that I could write an equation that is just 12x squared minus 30 equals 51. The end result will be the same. All right. Bring maybe 51 over here. Maybe I could factor this. Maybe I could take advantage of zero product rule. It is quadratic, right? So 2. So if this is positive, to justify moving it, I'm going to subtract. Right? Which means that this is going to be 12x squared minus 81 is equal to 0. That looks promising. Right? if I have 12x squared minus 81 equals 0, let me attempt to factor it now that I have introduced the extra guts to it. 12 is not going to work with these, but these are both divisible by 3. So that's their GCF, right? How do I know? The common factor, these are the factors of 12 at least. Everything is made of 1. Evens are all made of 2. This is not an even though. 6 isn't going to work with 81 though. Right? If you divide 81 by 6, and in theory you could divide anything by anything, it isn't divisible, so I'm not going to have a nice whole number. I'm going to get some decimal perhaps. Okay? And 12 doesn't work. It is, in fact, 4 won't work. Right? It's 3. So that's the GCF. Right? If I take out 3, it's just coincidentally what had been combined. This would be 4x squared, and this would be 81 divided by 3 is 27. Now you might say, hey, is that the difference of 2 squares? I wish, but it isn't going to happen in this case because 27 is kind of an annoying number. It's not itself a perfect square, so I'm kind of stuck with this. Right? I'm going to use the zero product rule now. So, if this is realistically 3 times 4x squared minus 27 equals 0, and it's factored now. Right? I could also move this 3, just to do myself the favor. Divide by 3, and now I have this 4x squared minus 27, this is still 0. Move 27 back. I know it's tedious, right? Here, add. And now you have 4x squared is equal to 27, divided by 4. And you have x squared is equal to 27 over 4. If you have something raised to an exponent of 2, in order to solve for this, to just get it to be x, you can perform the opposite operation. The opposite of squaring is to square root. Since you have a rational expression on the opposite side, remember that each one of these things is covered by this. And then there's a quotient rule of radicals, which says that if it's a convenience for you, you could break this up into 2 radicals and deal with them separately. X is the square root of 27 independently over the square root of 27 over 4. At least the square root of 4 is a regular number, right? It comes out. So the answer is this. X is equal to plus or minus, you get 2 answers for a radical, right? 27 over 2. All right. You know what? You actually can factor this. Let me do this a little bit further. All right. Ideally, you want to put this in simplest form. So in the case of 27, you want to break this up into, this is ideally, the highest perfect square possible, and then a leftover, all right, which is usually a prime number or a composite that would be impractical to factor further. Think of the factors of 27, 1, 3, 9, and 27. Everything has a perfect square that is 1, but we want the highest. 9 is a perfect square, so that's 9 times 3. What is just the square root of 9 by itself? 3 by itself. So this is, in a more reduced fashion, this would be a better answer. Plus or minus, because we're dealing with square roots. So there's 2 answers. 3 times the quantity, square root of 3, that's really 27 reduced over 2. That's the answer. And that is choice D. Okay? All right. Anyhow, that is everything up to this point. All right. Again, I'm not collecting this, I'm just going to give you credit for it, but for the sake of experience, All right, maybe check this out. You have all the answers now to practice, okay? This is what I considered the most important material out of what we've been covering. All right? Not that things are, you know, unimportant. I just consider this imperative. All right. Anyhow, all right. Fundamentally, I should say, most importantly, you want to do your homework. All right. So please bear in mind. I'll give you the credit for the test, but you got to do. All right. Section what was it 6.5 and 6.6. All right. By Thursday morning. All right. Okay. All right, thank you guys for sticking with me. Be careful out there.